Me čuješ?
Čujem.
Stavit ću snimak predavanja. Hello to everyone. Now we have to switch to English. Okay. I said that I will record this lecture, so just to know that if you ask some questions, maybe you'll be recorded. If this is okay with you. If it's not, then I'll just stop recording. Ivan, is this okay with you?
Yes, it's okay with me.
Okay, then Josipa, is this okay with you? And Philip also.
Yeah, it's okay.
Okay, great. What's going on in Sweden?
Nothing much. It's well, I think everyone stays at home.
Okay.
Like in Croatia as well, I guess. So it's quite calm here, I think, but people are still worried about COVID, so nothing much really.
And lectures, you have online lectures also on the university, yeah? All stuff.
Yeah, I think yeah, everyone has online lectures, so it's mostly like video lectures and work at your own pace at home.
It will go with exams, do you know maybe?
The SEM course that I have at KTH, or yeah, it's finished. So I finished it well at the end of December.
Ah, okay. You have trimesters, not semesters, yeah. So you're over before Christmas and New Year, or how it goes there?
I'm sorry. What?
So sorry, you have you don't have semesters. You have trimesters, or how do you call them? It's smaller.
Yeah, we have periods. So it's like 4 periods in 1 year.
Okay.
And so the second period, it ends in, well, I think in the beginning of January. So
Okay.
this, well, I think the third period has started now, but since I will do my master thesis, I just shifted it 1 month.
Ah, okay, okay. Josipa didn't answer it. So Josipa, is it okay if I record lecture?
It's okay.
Ah, okay, great. I thought that maybe you're sleeping and you just turn on Teams and continue to sleep, but fine, okay. Okay, so today we'll start with finite elements. Finite elements is a really big topic about numerical solving models. But we'll try in one lecture to explain basic idea about finite elements, and we'll construct 1D problem and construct a whole algorithm for a 1D problem. And at the end, I'll just show you the basic implementation of a 1D finite element method, or finite element method for a 1D problem. Okay. But at the beginning, some kind of meta stuff. Okay, I'll just bring it a little bit. Is it okay now? Do you see the whole blackboard?
Yes.
Okay. Okay. So finite elements. Okay. Fine. Letters are big enough.
Yes, yes.
Okay, great. So finite element method. It's a method of solving PDEs. PDEs are partial differential equations. You've seen some of them. Okay, what is the basic idea of solving PDEs? We'll look at a very simple model. We'll look at the Laplace problem, which is minus u is equal to f. It's like electrostatics. if you look at the Maxwell's equations, you know that the divergence of epsilon 0e is equal to rho, and if epsilon is a constant, so you can put a constant outside here, okay? And electrostatic rotation of electric field is equal to 0, which means that electric field is equal to minus gradient of potential. And if you put this inside, you will get divergence of minus gradient of phi is 1 over epsilon rho, and divergence of a gradient in minus Laplace. E is 1 over epsilon rho. So this is a basic, this problem is just a basic electrostatic. So that basic electrostatic problem can be written like this one. You can always put a constant inside the function and whatever else. So this is the reason why we will look at this simple model in order to introduce finite element method in the problem. Okay. Together with a problem with the PD, we need a boundary values. So we'll assume that U here is equal to 0 on the boundary. What does it mean? It means that if we have, I don't know, some kind of a domain called omega domain, so here inside minus Laplace of U is equal to F, but here on the boundary, U is equal to 0. So U is equal to 0 on the boundary. This is the standard notation for the boundary, and in omega. And in order to solve the problem, now we have somehow to discretize this stuff. So partial differential equation together with boundary values will combine together to get the problem. So usually this is called BVP, or boundary value problem. Boundary value problem. Okay. And finite elements is a way to discretize boundary value problems. There are other methods in order to discretize boundary value problems, like finite differences, and you can also discretize boundary value problem using boundary element method or method of moments. It depends how they call it, and similar stuff. But we'll see why we use finite elements to solve some problem of this kind, and how we can construct finite elements. Okay. So at any moment, if you have any question, just stop me and ask whatever you want. We will discuss everything. Okay. So what is the general idea of any numerical methods? If we have this kind of problem, idea is to somehow discretize the problem. And we'll end with a matrix times unknown is equal to the right-hand side. And we can solve this problem using, I know, any method of solving system of linear equations. So the stupidest one is to find directly the inverse of this stuff and say U is inverse F if there is an inverse. Okay, but if a problem is well posed, then there is an inverse of a matrix. Because if a real problem is well posed, we can show that this discretized problem is well posed. It depends on the method. But we'll use the method such that this will be well posed, and then we can solve this stuff. We will see that there is a lot of different methods how to solve this system of linear equations, iterative methods, approximative way of constructing the inverse, and other stuff. Because usually to find an inverse, you need something like n to the third power of operations. Finite element method is a way of constructing this matrix. We will see that somehow from this problem we'll construct similar problem, which is called weak formulation. And from weak formulation, we'll construct this matrix. What is the weak formulation? Now I'll just write it, and later I'll show how we can obtain weak formulation. Maybe we can start concretely. Okay, so example. We'll work on this problem, but in one dimension. So minus u prime prime is equal to f on 0, 1, and u of 0 is equal to u of 1 is equal to 0. So this is basically in any dimension, and this is in 1D. Example 1D. And for this 1D problem, we'll construct weak formulation, we'll construct this matrix, and we'll show the basic implementation of finite elements. Okay. Is this clear for now what will be our goal? So our goal will be to solve this problem using FEM, but between using FEM and solving this problem, we have to construct equivalent problem, which will be called weak formulation. There are different ways of constructing finite elements. One of those are weak formulation. It's very popular because it's easy to analyze it and see a priori what will be the error and other stuff. This is very hard from this formulation. There is also a minimizing formulation of variation of formulation in which you try to solve some minimizing problem. So there are a couple of different formulations of the same problem. Usually this one is not so physically motivated, because in physics, usually on the right-hand side, you don't have continuous functions. You can have, I don't know, impulse function, which is I would say Dirac, or you can have something which is discontinuous, because, I don't know, before this moment, everything, you don't have a load, and after that, something jumps and similar stuff, which is just an approximation. It's not possible to jump at one moment, but okay. We cannot use this kind of loads or right-hand sides in this formulation. Also in this formulation, we cannot use epsilon, which is not continuous. But this is quite normal to use epsilon, which is not continuous, because you can have one material, epsilon 1, and then second material, epsilon 2. But if we have different kind of epsilons, it will be inside the derivative. Because looking at the standard way of writing stuff, we will have epsilon here, a plus of potential minus is equal to f. But this is not continuous, and we have to take a derivative of something which is not continuous, and it's not defined well in this kind of formulation. This is the reason why we have to use weak formulation, because it's more physically motivated than any other formulation you can look on. This kind of writing differential equations, which is a way how you learn differential equations on your studies, is well, nice stuff, but not so applicable to physical problems. Okay. How we define so-called weak formulation? So weak formulation. What is the idea? Test your problem. Using test functions. So what are test functions? So you can think of test functions as some kind of glasses through which you look at your problem. So if you go to measure something, you cannot take point measure on every point of the domain. It's not possible. So you have some real not equal to 0 point of your measurement equipment, which you have to put somewhere, and then you measure some point, not a point, but portion of space what's going on there, and then you just approximate the values on that point. So basically, you have to look at your problems through a measurement equipment. And test functions are just like measurement. Okay. So we have minus u prime is equal to f, u of 0 is equal to u of 1 is equal to 0, and this is in 0, 1. So idea is to test these test functions, which means multiply this with some function we call test function, and then integrate over 0, 0, 1. Okay, so 0, 1 minus u prime x phi of x dx is equal to integral of 0, 1 f of x phi of x dx. Okay. Here we can use integration by parts. And write this as minus u prime of x phi of x at the boundary 0, 1 minus integral of 0, 1 of minus u prime p prime dx. Okay. At point 1, u is equal to 0. It's our boundary value. At the point 0, okay, this is u prime. Sorry, no. We have somehow to eliminate this kind of boundary stuff. We know that u of 0 is equal to 0 and u of 1 is equal to 0. But here we don't have u of 0 and u of 1, we have u prime. So derivative of u at 0 and derivative of u at 1. And we don't know if this is equal to 0. Okay? But we can pick test functions in a way which best suits our problem. But if our u is equal to 0 at the boundary, so 0, 1, and u as a solution is equal to 0 here. We don't know how it looks like, but here will be 0. Okay? In order to test what's going on here, it doesn't make any sense to use phi which is not equal to 0 here. Because our solution is equal to 0 here, we can use test function which is also equal to 0 at boundary points. So we will not use any test function, we will use test function such that phi of 1 is equal to phi of 0 is equal to 0. Okay? So using these test functions, this is equal to 0. And we'll just let with this portion, which is equal to integral 0, 1 u prime of x phi prime of x dx, which is equal to the right hand side 0, 1 f of x phi of x dx. And this will be the problem we'll try to solve. This is called deep formulation. So we see that here we have a second derivative of u, and here we have a first derivative of u. So we need less smoothness of a solution. But also, if we had epsilon inside, so problem looked something like epsilon u prime prime, after the integration by parts, we'll see that epsilon goes here. And we don't have any derivative on epsilon. So epsilon can be discontinuous. Because if epsilon is discontinuous, we just have to integrate over this continuous function. This is not a problem. We can integrate this continuous function without any problems. So this is the way why this is called weak formulation. Because somehow we need weaker assumptions on our solution in terms of smoothness, but smoothness and continuity is already, so it's just a smoothness parameter. It's just a smoothness, but the basic smoothness you can have. So here we just need weaker assumptions on the smoothness of our solution, and also we can put, as I said, epsilon inside, so any parameter we want, which is discontinuous or whatever else. And also, if f is equal to, well, Dirac distribution, whatever it means, here we will have a Dirac inside an integral, which is somehow well defined. We know how to work with that. But here, if we have a Dirac on the right-hand side, and we need something which, after taking derivative, will give Dirac, it's a little bit problematic. But here it's not. So basically, in this kind of formulation for problem, you can put discontinuous parameters inside. You can put Dirac on the right-hand side. You can use right-hand side, which is not a continuous function, which can be just a jump. Because if f is jump, there is just a jump inside an integral. Who cares? You can always integrate this continuous function. Okay. Is this clear for now? So what we made is transformation from minus u prime prime of x equal to f of x in 0, 1, u of 0 is u of 1 is equal to 0. We define so-called weak formulation. Integral of 0, 1, u prime of x, p of u prime of x dx is equal to integral 0, 1, f of x, p of x dx, where p phi of 0 is equal to phi of 1 is equal to 0. And here, as I said, we have less smoothness assumptions on mu. We can put f, which is discontinuous or whatever we want. We can put discontinuous parameters and whatever else. An idea will be to discretize this problem. So idea, discretize weak formulation. Because this is also continuous problem. So this is continuous problem, this is also continuous problem, but we have to go to a discrete problem. And we'll discretize this stuff. Usual way of discretizing stuff is the idea is to introduce so-called finite element space. But we'll go try to describe things in steps. As in any discrete problem, we have to define so-called mesh or grid. So 0, 1, we'll define points here such that x0 is equal to 0, and goes x1, x2, x, the last one I call it xn. So we have points 0 is equal to x0 less than x1 less than x2 less than xn minus 1 less than xn, which is equal to 1. So we divided interval 0, 1 into these points. And we have n plus 1 points and n minus 1 intervals. Here. And this point xi, so this is xi, we call it a node. Node or nodal point. Okay. And this small interval xi plus 1 is an interval we call E. Okay, and what we have to define? We have to define h. Small h is maximum over hi for all I, where hi is just xi plus 1 minus xi. It's the length of this interval. Length of. And this h will describe how crude is this mesh. If h is smaller, that means that these points are closer and closer. If they are closer, we can expect better approximation of our solution. It always goes like that. So if you want a better approximation, you can work with bigger amount of discretizing points, but smaller intervals between 2 points. Okay. And the idea will be if we have 0, 1, and some discretizing points, and we know that our solution looks like this. Idea will be to approximate this solution using some kind of finite elements, which means some kind of discrete approximation. And here, our discrete approximation, we will use linear elements, so our approximation will be somehow linear. Okay. We'll see what it means to approximate something with finite elements. It doesn't converge in points; it converts in energy, which means that what is the energy? Energy is just integral of your solution. So 0, 1. U squared dx, we'll see that approximation of finite elements somehow, idea when we put more and more elements inside will somehow make this difference between U and U approximated, or U FEM squared, which is the energy in the difference between the real solution and approximation of solution, somehow goes to 0 when h goes to 0. So we don't have approximation in points, but we have approximation in energy, in terms that the energy between real solution and approximated solution goes to 0. Okay. And now we have to define finite element space, and other stuff. Okay. Our solution U comes from some function space. So you had some kind of linear algebra, you know what is a vector space. Function space is a vector space of functions. Okay. There are a lot of different vector space of functions. Some of them is, you know that from signals and systems, it's L2 functions. What are L2 functions? It's just function 1, 0 to R, such that they have finite energy. U squared dx is smaller than U. Okay. This is some kind of a function space, because if you take two functions from here, one have a finite energy, second have a finite energy. If you add them together, they have finite energy, and if function have a finite energy, if you multiply it by 10 or some constant, it will also have a finite energy. So this is some kind of function space. And in all these big formulation problems, solution comes from some kind of function space. And the idea of finite element space is to find discrete approximation. Discrete approximation of some function space. Okay. Which one? Well, it depends of a problem. It depends of a problem you are solving, which function space you need. And according to that function space, we will use your discrete approximation of our finite element space. And these are usually, I don't know, linear finite elements, cubical finite elements, discontinuous finite elements, whatever you want. There's a whole zoo of finite element spaces you can use, but according to the function space in which your lead formulation is defined. And this will be just for your information, don't bother yourself with that. But this problem 0, 1, 0 prime of x, phi of x, if x is equal to 0, 1, f of x, phi of x, dx. Okay. Here, phi prime, here u is not from this L2, because here we need that u has a finite energy. Finite energy, and u prime has a finite energy. So we need u such that u has a finite energy, u prime has a finite energy. So somehow that u is from L2 and u prime is from L2. This is called some kind of sort of space H1. Okay. This is just for your information. If you will ever read something about finite elements, you will see standard notation. And here our function u is equal to 0 on the boundary, so this is usually called k01, h01 on 01. Okay. And we can approximate this solution space with some kind of finite element space, and we will use in our problem in order to show what's going on. We will use first order polynomials or linear elements in order to approximate our solution, which comes from this space, which is just a short notation to say that u and u prime has finite energy. Okay, it's more than that, but basically it's not important now. So u as a solution comes from some function space called h10, 01, and finite element space is finite dimensional space used to approximate functions from H01, 0. So theory is bigger than that. We have to know, is it possible with our finite element space to approximate all functions here? It's a very big problem. It's a very big problem in electromagnetics, because you cannot use in electromagnetics any function, any finite element space you want. It's proved 20 years ago that there are spurious solutions. You have spurious eigenvalues of a problem, solutions which doesn't exist if you use some kind of finite elements. If you use, I don't know, linear approximation of electric and magnetic field, it will generate solutions which doesn't exist. So to pick finite elements for your problem, you have to know how this behaves. Okay, and problems for Maxwell's equations are, well, not so easy to explain in a couple of sentences. But there are so-called metallic elements which are okay for discretizations of Maxwell equations. So if you will ever write your own finite element code for solving Maxwell problem, you'll just pick metallic elements. Usually use some kind of a library to construct finite elements, and in that library, like Phoenix, FEM, Dune, or some else, you have metallic elements implemented. You just have to call those elements. But you have to know that, because if you want to solve electromagnetic problems and use like linear elements, probably you get spurious solutions. Okay, as I said, U is from some function space, but we will try to find U FEM from finite element space. Okay, and this is finite dimensional, so dimension of each space in smaller than plus infinity, so it's finite dimensional, so it has a basis. And because this finite element space has a basis, we can always write this UFEM in terms of basis elements. And we made our interval divide in n-1 subintervals. So using P1 elements, our P element space, so using linear finite elements, dimension of our finite element space will be equal to n-1. So we can write our solution, UFM, in terms of some j is equal to 1 to n-1, alpha j Pj. What is Pj? Basis elements. So our basis is P1, P2, Pn-1. We'll describe that basis soon. And these are coefficients. An idea of solving system of linear equations is to find those coefficients. And when we find these coefficients, we can just describe our solution as ordinary linear combinations of basis elements and coefficients. So the whole idea is to find these coefficients. But this is a linear algebra problem, basically. You learn that when you learn vector spaces, how to describe a vector in a vector space, or some other problem. Okay, which basis can we use? As usual, what is a basis? Basis is just a number of linear independent elements which can describe all other elements in space. But as I said, this is just a linear algebra stuff. And we will use so-called P1 elements. Okay, what are P1 elements? Pj is a linear function. Okay. Is it clear for now what is the idea of all this my gibberish talk? So idea is now, so we have a reformulation. We'll approximate our solution using finite element space. That space will be P1 finite element space. which means that our basis functions are linear functions. We'll find all the linear functions describing this discretization and construct matrix for the system of linear equations. Because here we have big formulation, u prime of x, t prime of x, dx, and we just have to put this stuff inside, okay? And then test with test functions, but also from, so using test functions from the same space, from the same finite element space. Okay. You don't have to do like that. You can use test functions from some other finite element space, but in that case, analysis is harder, convergence and all other stuff doesn't have to be well posed. There are a lot of different problems. But if you decompose your solution in the same space as test functions you are using, it's called usually Galerkin method. So they're calling him Galerkin or something like that, but he's Russian, so it's Galerkin. Galerkin method. So using the same finite element space for your basis and test functions. Okay. Next step, put this inside and calculate coefficients. Calculate the integral near your coefficient alpha j. Okay, so we have a couple of more minutes before the break. I'll just do the Blackboard and put this inside. Okay, so we have 0, 1, u prime of x, t prime of x dx equal to 0, 1, f of x, t of x dx. Okay, but we want to test this in the finite element space, so we'll write this for, not for phi, as any test function in our finite element space, but in our finite element space we have a basis, so we can test this for all basis functions in basis of our finite element space. So we'll say Fi for one smaller than I smaller than n minus 1. Okay, so now we have n minus 1 equations. In first one is the first basis element. In the second one is the second basis element here and here, and so on. Later we'll describe how those basis elements look like, but for now, we know that we can write n minus 1 equations. And here we'll plug inside our FEM, decomposed in terms of basis elements of our finite element space, which is J is 1 for n minus 1, alpha j, j. So if you put it inside, and we know that the integral is a linear function, so we can put coefficient and summation outside, we'll get j is equal to 1 to n minus 1, alpha j, 0, 1, tj prime of x, ti prime of x dx is equal to 0, 1, f of x, ti of x dx for 1 less than I less than n minus 1. What we have here, now we have one linear equation because we have n minus 1 unknowns, so we can always write integral 0, 1, phi 1 prime, phi prime times alpha 1 plus integral 0, 1, P2 prime, I prime, alpha 2 plus integral 0, 1, phi m minus 1 prime, Pi prime times alpha m minus 1, and this is equal to integral 0, 1 fx, Pi of x dx. And this is one linear equation with n minus 1 unknown, and we have n minus 1 less than I less than n minus 1 equations. So we will end with a problem A alpha, which alpha vector is a vector of unknown coefficients, alpha 1, alpha n minus 1. But we know how to construct A because we know which basis function we pick. We will pick linear basis functions. And on the right-hand side, we know we can integrate. We know our right-hand side function, our load, and we know our basis functions. And basically, we can construct everything from this point. And the main basic idea was to use finite dimensional approximation of our solution space. In that finite dimensional approximation, we can find the basis. Because we can find the basis, we can decompose our solution we are searching for in terms of that basis. We can plug in that basis in our big formulation, and using just ideas from, I don't know, integration, whatever, at the end with standard linear algebra problem, A alpha is equal to F vector, where F vector is just a vector of these integrations. 0, 1, F, 3, 1, 2, 0, 1, F, 3, and minus 1. Okay, we'll have a small break, and next hour we'll construct A from, we'll first define our basis. When we define our basis in linear finite element space, we'll construct from that basis, we'll construct our matrix A, and from construction of matrix A, we'll end with system of linear equations, which we'll try to solve using some kind of a method. Here I just implemented 1D problem, so we can use direct method. It will finish in, I don't know, less than a microsecond, but in a 3D or something like that, it's much bigger stuff. Okay, let's have a break. I'll come in 15 minutes to continue journey through finite elements. You can ask me a question if you want to ask something. Just don't hesitate. Okay, can we continue with the finite element stuff? Do you have any questions before I start to develop FEM? Are you alive? Do I have to call an ambulance? Okay. Okay, just to remind you, we started with u prime is equal to f, u of 0 is u of 1 is 0. Then we constructed a big formulation, 0, 1, u prime, phi prime is equal to 0, 1, and phi, such that phi 0 is phi 1 is 0. And then we plugged in, so I argumented a little bit that this u is from some function space, and that we want to approximate that function space with some finite element space, which is finite dimensional space. We know that finite dimensional vector space has a basis. We can write our solution in terms of basis elements. J is 1 to n minus 1, alpha j to j. This m minus 1 basis elements is connected to P1 elements. Okay. And then we just plugged in this inside and tested with phi, and then we get j is 1 to n minus 1, alpha j, 0, 1, pj prime, pi prime is equal to 0, 1, f I, 1 smaller than I, smaller than n minus 1. So we started with some kind of continuous formulation. We get a big formulation. I argumented why is big formulation better suited for physical problems because we can treat discontinuous parameters, we can treat discontinuous right-hand side, or even the delta function. Okay, and then this is better to use in finite element approximation because we know that this u comes from some kind of function space, and we can approximate that function space with some finite element space, which is finite dimensional. Write your solution in terms of basis, put that inside, and now you just have to calculate this, and you will have the whole matrix. Okay, P1 elements. What are P1 elements? Phi I is a linear function. Okay, defined on every portion or on every subinterval from the class discretization. So it's defined like Phi I of xj. So 0, x1, x2, xn minus 1, xn is equal to 1. This is xj. Okay, and phi I is I basis function evaluated at the point xj. And this is equal to 1 if I is equal to j, and 0 if I is not j. Okay. What does it mean? That means that we have basically a head function. So this is xi plus 1, xi minus 1, this is 1, and our Pj, Pi looks like this. Okay, this is Phi. Phi evaluated at point xi is equal to 1, and in all other nodal points, so xi equals 2, xi minus 2 is equal to 0. Okay, how can we write our Phi? Well, it's just a basic linear function. It's equal to 0 if x is smaller than xi minus 1. Here we have a growing linear function, so it's x minus xi minus 1 over this length of this subinterval, which is xi minus 1 for xi minus 1 smaller than x, smaller than xi. Here we have a decreasing linear function. We just xi plus 1 minus x over xi plus 1 minus xi for xi smaller than x smaller than xi plus 1 and 0 for x larger than xi plus 1. But the function is continuous here is equal to 0. So it's smaller than, bigger than. Okay, this is our linear basis function. And now we have to find the derivative of this basis function and plug in that into this formulation. Okay. But these are not the all basis function you can use. There are a couple of ways how to define basis functions. You want functions that are simple, as with compact support. What does it mean? That means that function is greater than 0 just on a compact space in one dimension, just over subinterval, and they're smooth in some way. Here, those are continuous. As I said, for the electromagnetic problems, we will use network elements, which have some continuous tangential components, similar stuff. Okay, so we'll use this function to define primes and put that into the formulation to obtain our matrix. So matrix generating matrix A. It's called stiffness matrix. So stuff. We've seen that when we plug in finite element solution, we get J is equal to 1 and minus 1, alpha J integral 0, 1, Pj prime of x, I prime of x dx. But this would be ij component of a matrix. So that our matrix multiplication is written J is equal to 1 to n minus 1, aij alpha j. So aij is integral 1 to 0, Pj prime of x, Pi of x, Pi prime of x, dx. Okay. So matrix A is matrix of all those elements. I, A, K. And we can write this element, this number as 0, 1, Tj prime, Ti prime, ds. But we can decompose this integration over subintervals. 0, x1, x2, xn is equal to 1. So write it as 0, 1, 0, x1, or x0, x1, Tj yi plus x x1 to x2, Tj prime, Ti prime, plus xn minus 1 to xm, Tj prime, Ti. Every element, so every small element of a matrix we can decompose in this way. And why we want to decompose that in that way? Because our cat function, say xa minus 1, xa plus 1, is not 0 only here. So a lot of these integrals will just vanish. Okay? So if we look at the x of, if we look at phi I basis function, then integrals on x0 to x1 will be equal to 0. x1 to x2 will be equal to 0. Only integrals over xi minus 1 to xi and xi to xi plus 1 will not be equal to 0, because only on this portion our basis function is not equal to 0. So basically a lot of this stuff will be equal to 0. We'll see that in a moment. Okay. So if you look at the beginning of a matrix, you have integral x0 to x1, phi1 prime times phi1 prime. So it's phi1 prime squared. Then you have integral plus integral over x1 to x2. Okay? But we'll decompose this in a second matrix, in a matrix which looks like this. So here we have x0 to x1, phi2 prime, phi1 prime. Here we have x0 to x1. So in the first matrix, we'll just put integration over x0 to x1. Then plus second matrix integration x1 to x2. Then plus plus plus. In the last matrix, we'll put integration xn minus 1 xn. Why will we decompose our matrix in this? Because in that way we'll construct our algorithm. Because we'll just make a loop around 0, x1, xi, xi plus 1 plus 1, xn. So we'll make a loop through all these subintervals, and on the first subinterval, we'll just integrate over the first subinterval. But here, everything will be equal to 0 except this sub. Then we loop to the other subinterval. Integrating on the second subinterval only functions. So here we have this basis function, and which is phi1. Here we have a second basis function, which is phi2. So integrating on this subinterval, we just integrals with phi1 will survive. Integrating on second interval, only integrals combining phi1 and phi2 will survive. Going to the next one, this is phi3, x3, blah, blah, blah. Going to the third subinterval, only these only integrals with phi 2 and phi 3 will survive. So basically, all this matrix will have just this element, because phi 2 is equal to 0 on this subinterval. All this matrix will have just 4 numbers, because here we have x1 over x2 phi 1 prime squared. Second number in the second a1, 2 place, we have x1, x2 phi 2 prime, phi 1 prime, and this one will be 0. A1, 3 will be 0 because in this subinterval phi 3 is equal to 0. And here you have x1, x2, phi 1, phi 2 prime, which is not 0, and on the place A22, you have x1, x2, phi 2 prime squared. These are the only non-zero elements in m-1 times m-1 matrix. Okay? And then in the third one, you have only 4 numbers not equal to 0, and those numbers will be the numbers combining phi 2 and phi 3. And in the last one, only those combining xn minus 1, xn, only xn minus 1, because here, as I said, all these are 0. And in this decomposition of a matrix A, you can see how you construct an algorithm. So loop over all subintervals. On the first subinterval, construct a local matrix and put it in the global matrix. Go on the second subinterval, construct a local matrix, put it in the global matrix. Third one, construct a local matrix. Local matrix is just those 4 numbers. And you put those 4 numbers in the big matrix on a place ij. Okay? And when you loop over all these subintervals, at the end you will have constructed our global matrix. Okay. And this is a standard way of constructing finite element procedure, because you just loop over elements, construct the local stuff, and then just make a local to global transition. Just describe that in a moment. So what is a local stiffness matrix? Local matrix. I'll call it A. E. So it's connected to the element or to the subinterval E. So xi plus 1 for this. I think so. We have only 4 numbers. It's a 2x2 matrix. It has integral over xi plus 1 of phi I prime squared dx. Yeah. And then xi plus 1 is phi I prime, phi I plus 1 prime dx. Here it's just the opposite, xi plus 1, phi I plus 1 prime, phi I prime, and the two number is xi plus 1, phi I plus 1 prime squared. Okay, so this is our local, we call it stiffness matrix. Matrix A is usually called stiffness matrix. Terminology comes from the elasticity theory, where stiffness means something for the deformations. Okay, and now we have a local matrix A, and we just have to match this into the global matrix A, which is n minus 1 by n minus 1 matrix. And then we put on A plus 1A portion in our big matrix. So we come to this element, calculate local stiffness matrix, and finish our loop on this element just to put these numbers whenever we have to put it in a bigger matrix. And then go on the other element, calculate local stiffness matrix, put that local stiffness matrix inside. And looping through all elements, we'll calculate all local matrices, we'll put in a global matrix, and that way we constructed global matrix. So algorithm. So for, I said, I is 1 to n minus 1, calculate local matrix, and then put those elements, those numbers in global matrix. And in that way, we constructed matrix A, global matrix A. Okay, how did we construct the right-hand side? Right-hand side vector. As remembered, it's equal to 0, 1, f of x, phi I of x, dx. Which can be decomposed in terms of those x0, x1, x1, x2, xn minus 1, xn. But we know that phi lives only on the xi plus 1, xi minus 1. So here, on the ith component, we will have only integral xi minus 1 to xi, f phi I plus xi to xi plus 1, f all other will be equal to 0. So while we're looking through the elements constructing local stiffness matrix, we'll just construct a local load matrix. So on this element, we'll calculate integration on this portion. I'm going to the other, we'll integrate on the second one, I'll just put in the global positions. Okay, so now basically we know how to construct stiffness matrix and the right-hand side. We just have to plug in P1 elements to see how matrix looks like. Okay. So xi plus 1. We know that here we have phi I. Here we have phi I plus 1. Okay. And this is the subinterval E. So phi I on subinterval E is a decreasing function. We just xi plus 1 minus x over xi plus 1 minus xi. And in order to calculate local matrix, we need a derivative of this. So phi I on the ith interval, if we take a derivative, we have just x here is minus 1 over xi plus 1 minus xi. And we call this hi. So it's minus 1 over hi. And phi I plus 1 on the subinterval E is increasing function. It's x minus xi over xi plus 1 minus xi. So if you take a derivative, phi I plus 1 E, derivative is 1 over xi plus 1 minus xi, is 1 over HI. So local stiffness matrix. So A. So on the element A, we have to integrate over xi to xi plus 1 di prime dx. And then this, okay, I'll just write those integrals and then put it in the matrix, it will be easier. So here we plug in xi plus 1 minus 1 over hi squared dx is 1 over hi squared times hi is just 1 over hi. Say xi plus 1. So this by I prime by I plus 1 prime dx is integral xi plus 1. To calculate those derivatives is minus 1 over hi times 1 over hi dx. But when we integrate, we'll get an hi. Just turn this down, and at the end we'll get minus 1 over hi. So local stiffness matrix 1 over hi minus 1 over hi minus 1 over hi 1 over hi. Okay. And now we just have to this local stiffness matrix map to a global matrix. Okay, so looking through the elements, calculating local stiffness matrix, mapping to the global one, we get A which is equal to, so this is the big matrix. So first is 1 over H0 minus 1 over H0 minus 1 over H0, 1 over H0 plus 1 over H1 minus 1 over H1 minus 1 over H1 0. And on the diagonal, you have a summation 1 over length of the previous interval together with length of this one. So here we have minus 1 over Hn minus 3, 1 Hn minus 3 plus 1 over Hn minus 2, minus 1 Hn minus 2, minus 1 Hn minus 2, so this is 1 over Hn minus 2 plus 1 over Hn minus 1, minus 1 over Hn minus 1, minus 1 over Hn minus 1, and 1 over Hn minus 1. So this is our global matrix. All other coefficients are equal to 0. Okay. And if all Hi are equal and equal H, you'll get 1 over H minus 1 over H minus 1 over H, 2 over H, 2 over H, minus 1 over H, minus 1 over H, 2 over H. Is all of this, all Hi are equal, this will be our stiffness matrix. But you've seen this matrix in the finite difference method. So approximating, we are solving the same equation. So approximating that I would say, Laplace problem in one dimension with P1 elements and finite differences, again, you have the same matrix for your system of equations. This is just for the P1 elements in this problem. Okay, so now we have everything. We just have A alpha is equal to right hand side. We reconstructed A, as I said, 1 over h, minus 1 over h, minus 1 over h, 2 over h. And if we plug 1 over h outside, we have a standard 1, minus 1, minus 1, 2, minus 1, minus 1, blah, blah, blah. But we have to plug out, so we have to put in the boundary value, so we plug outside first and the last row. Okay. What else to say? Now we just have to solve this system of linear equations using some kind of a method. So because those matrices are three-diagonal with a lot of zeros, you can use iterative method to solve the problem. It will converge in some kind of n steps, but using the standard finding way of inverse, not approximate inverse, but real inverse, it's like n to the third power of operations and some iterative method. And Jacobi, you can parallelize Jacobi, Gauss-Seidel, you can parallelize Gauss-Seidel, but you can use it, it will converge in some kind of n steps or n log n, something like that. Okay. Now we have to see how implementations look like. Okay. Okay, do you see MATLAB now?
Yes.
Okay, great. Okay, unfortunately, I've written this code in Croatian, but I'll explain everything in a second. So if you see here, we have a problem minus second derivative is equal to f, which is our problem. U of 0 is equal to U of 1 is equal to 0. Okay, on the interval between 0 and 1. Now here we have boundary conditions. So left side is equal to 0, and boundary condition is equal to 0. Right hand side of an interval is 1 because we work on 0, 1, and right hand side boundary boundary condition on the right end of the interval is equal to 0. And we have some kind of load function. It doesn't matter. And what is the idea? Idea is loop over all elements. So we have some number of elements, go to all elements and construct local stiffness matrix and local right-hand side load. And then when you constructed local matrix, you just have to put that local matrix, A loc, into the matrix A, which is a global matrix. So on a position I yacht, you will put the right number from the local matrix. So basically this is the whole finite element procedure. And when you loop over all elements, you also have to construct right-hand side. So from constructing local right-hand side vector, you just have to put that in a global right-hand side vector. And this is for P1 elements. So local stiffness matrix is, as we calculated, 1 over h on 1, 1 place, minus 1 over h, and minus 1 over h on 1, 2, and 2, 1, and 1 over h on 2, 2. So this is the whole algorithm, which is quite easy in one dimension for P1 elements. And when we run the stuff, so I calculated the real solution, exact solution, it's blue, and finite element approximation with red. And standardly, if we put less elements, we'll get not so good solution. And if we put more elements, I know 25, we'll get a better solution. When I said elements here, I mean elements into discretization, not finite elements. So here I said number of elements in the discretization. So usually people use the same name for different stuff. When we say finite element is just a finite element space. It's space for which we know how to describe basis functions and other stuff. Here, when I say element, I mean just the subinterval into the in the discretization. Okay, so this is the way how you can construct stuff in 1D. But usually you will not use, you will not write your own code because it doesn't make any sense. Okay. Hope that you can see me now. What is the idea? Idea is to use some libraries, and I'll just mention a couple of libraries which are really good for constructing finite elements. So finite element libraries. So what usually you have to do in a library using library? You have to define the formulation. Define big formulation, define finite element space, use appropriate linear algebra package for solving A alpha is equal to F. Okay, and you have to construct a mesh. And for constructing mesh, if you are trying to solve some kind of problem on a standard geometry, you can always use a mesher. A lot of these libraries has their own meshers. But if you don't, if you have to use some kind of fuzzy geometry, you can always use Gmesh. Gmesh is a really nice measure, free to use. You can find it on the internet. So. Okay, and when you construct mesh on Gmesh, you just use some library to define all this stuff. And library will calculate local stiffness matrix and match the global stiffness matrix for you, which is not so easy problem because, as I said here, we use P1 elements in one dimension, but when you use vector elements or other stuff, you have to lose too much time to construct that stuff. So we use library for constructing. So library will construct A for you. Matrix A. For that we use library. And in every library you have a lot of implemented lot of different finite element space. The best library, but not the best, but one of which I use often is Phoenix. Okay. There's a very big community of people using Phoenix. You have a lot of forums on which you can ask questions and other stuff. Second is Firebase, which lives on the same libraries under the hood as Phoenix. So those two are really great for Especially FireDrink is really great for solving electromagnetic problems because it has implemented complex numbers and other stuff you need. Phoenix implemented complex numbers recently in Phoenix X library. Then you can use all of these libraries you can use in Python. So they have Python library. Okay, and there are a lot of other libraries like FEM, Dune, DL2, and those are maybe, I don't know, the best I tried. And in Phoenix and FireDrink and FEM, this matrix is a library that just construct a matrix. In DL2, you have to construct it by yourself, but you have a lot. It's you have to work more in DL2 than in those two, but in DL2 you can do a lot of great stuff. I used Dune just on one exam I had, so I'm not so much affiliated with Dune, but it's also a really great library. And for method of moments, or boundary element method, as people usually call it, if you are trying to solve scattering problems, there is a FEM++ library, or FEM for Python. So this is a library for constructing approximations of integral equations, which are usual equations in scattering problems. So my idea for the problem I'll make for you for your exam is to use one of these libraries and construct finite element approximation of an easy problem, just to see how those libraries works. How can you construct some solutions inside? How can you construct a problem inside? How can you get a solution at the end? How you can visualize that solution and so on and so on. So basically, this is the I know fast introduction to finite elements, mentioning libraries which are great to use in order to construct your own finite element procedure. Now, if you have any questions, you can ask whatever you want. I'll try to make those problems today. I think the professor said that we would send you those problems today or tomorrow. Okay. So if you have any questions, ask now. If not, then this is the final lecture of this course. We'll just send you a couple of emails for all other informations. Thank you for watching. See you.
Thank you. Bye.
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 Bye.